We've looked at liquids and gases, and now we'll take a closer look at solids. Solids can be crystalline or amorphous. Crystalline solids are made of molecules or atoms or ions that are highly ordered. They usually have flat surfaces like quartz or diamond. And this is amethyst. It's a type of quartz. The word amorphous comes from the Greek, meaning without shape. Amorphous solids don't have an orderly structure. Examples of an amorphous solid are rubber and glass. Silicon dioxide, or quartz, melts at somewhere around 1600 degrees Celsius, at which point many of the bonds between the oxygen and the silicon will break. If we quickly cool the melt, the atoms don't go back until their nice orderly arrangement that you see here. Our new arrangement would look more like this, forming something we call silica glass. Sand can be high in silica or quartz. And remember we said that the melting point of quartz is somewhere around 1600 degrees. Well, lightning can strike at somewhere around 1800 degrees Celsius, and when it strikes the sand, if the conditions are good, then what can happen is the formation of an amorphous structure, fulgurite, which is basically hollow glass tube, also known as petrified lightning. It's pretty cool stuff. And since amorphous solids don't have that nice, orderly, stable structure, they're going to have intermolecular forces whose strength is going to vary throughout the sample. And so while crystalline solids with their nice, orderly structures are going to melt at specific temperatures, amorphous solids can melt over a range of temperatures. There are 4 different classifications of solids. The first is molecular solids. And remember, molecular means we have covalently bonded molecules. And the intermolecular forces that are associated with covalently bonded molecules are hydrogen bonds, dipole-dipole forces, and London dispersion forces. Now, all of these intermolecular forces, generally speaking, are pretty weak when we start to compare molecular solids to other types of solids. So, molecular solids are usually soft and have low melting points, below somewhere around 200 degrees Celsius. Many of them are organic compounds composed of carbon and hydrogen. And some examples of molecular compounds are sucrose, or table sugar, ice, or solid H2O, and dry ice, or solid carbon dioxide. The next type of solid we'll talk about is the covalent network solid. These solids consist of atoms in large networks or chains that are held together by covalent bonds. Remember that covalent bonds are stronger than intermolecular forces or attraction, so these solids are going to be harder and have higher melting points than molecular solids. Examples are diamond and graphite, both of which are allotropes of carbon, and are quartz, or silicon dioxide. The third type of solid we'll look at are ionic solids, which are ions that are held together by ionic bonds. The strength of the bond is going to depend on the charge of the ion. For example, sodium chloride, sodium having a +1 charge and chloride ions having a -1 charge, is going to melt at 801 degrees Celsius, while magnesium oxide, whose charges are +2 and -2, will melt at a whopping 2,852 degrees Celsius. You already know what sodium chloride looks like. These are some crystals of magnesium oxide. It's ground up and used as a nutritional supplement for supplemental magnesium in the diet. And finally, our last type of solid is the metallic solid. And they consist of all metals. And remember from our chapter on bonding that metallic bonds are delocalized, like a mobile sea of electrons that connect all of the neighboring metal molecules, atoms together. And since these electrons are kind of free-floating, this is the reason why metals make such good conductors of heat and electricity. And the more electrons that are available for bonding, the stronger the metallic bond will be. For example, sodium, with its one valence electron, melts at 97.5 degrees Celsius, but chromium, with 6 available electrons for bonding, is going to melt at 1,890 degrees Celsius.